everything that you do, so that you can explain code and talk about code to other developers and non-developers. So let me write this down. So today we will have the activity review of the trees, and then we will see graphs, which is the last of the structures that we're going to see. They are quite similar to trees, actually. And then we will do the exercise activity with the graphs, but we will do it in pair programming. Try to do pair programming this time. And so we'll get separated in groups. And yeah, so we will see about pair programming. You can use it. You can use some extension in VS Code to share your code with others so that you can both type, or you can take turns, which is also a good practice. So you share screen, and then once one function, maybe one person is doing it and the other is helping us, giving ideas. And then on the next one, you switch, and then the other one is writing. So we will work a bit on that so that we practice a bit of pair programming as well. Okay, so okay, Tatiana Case is here. Let's see, any volunteer for trees? We have normal trees and binary trees. You choose. We start with normal trees. How was it? Not that good.
I don't know. I think my brain is still coming off being sick, and I'm having some problems in general, but honestly, thinking about trying to figure out how to do the traverse stuff made me want to cry. And it was challenging. I figured out some of the simpler ones, but I had to step away. I was like, I don't know what I'm doing with my life. But I'm here now. I'm ready to go over it. And
okay. Any other feeling similar?
Yeah. It's linked lists all over again.
They are a bit better, I think. You don't have so many pointers. Okay, so anyone wants to start? Maybe you don't have to show the whole tree, just some of the functions, and then some other will take over. Okay, I will do my random selector program to randomly select some.
I can do, but for the tree, I did just 2 exercises, no more, because I didn't understand the rest.
Okay. Okay, sure. Just start with this, and we'll see. We see if someone else has done some extra. We can add that, and if not, I will show.
Okay, I will show you my. I need to able for the show the my screen.
Yes. Let me see, share screen. Yes. Okay, now you should be able.
Can you see my screen now?
Yes.
Okay, this is the tree. It was really difficult because I think this part is the most interest for me. And here I have the trees, and the first exercise, it was a child. It's not too much. I add the new tree. I create the new variable, the new tree, and is the new tree for the class. How do you say instance?
Instance, yes.
Instance, yes. Sorry. And just I put the push, and it's working. Okay. And for the contents, it's just
so this class, this method, the addChild method, is not returning anything. It's just pushing a new node that it's also a tree. So it just
Yes.
creates a new subtree with the value that we provide, and it just pushes it to the children of the original tree. Okay.
Yes.
Okay.
And the next exercise is just the return if it's true or false, if it contains the value. And just with the conditional value is the same, this value, and return true. Else, we need to, I put the function sum, and it was working for this. This is the test. One second. Oh, it's not working, but yesterday it was working. Yeah. And this is the test.
So this is the add child, and then for the contains, it should return true if the value is in the children. Okay, and so you add a child and then you test it.
Yes.
And then you add two childs and it's also testing.
And
yes.
And for this, it was really, really weird for me, this the reverse. I didn't
So the
understand.
contains, sorry, again, and the contains, you have, so the first that it checks is if the value is equals to this value. So on the line 23, we check like if the value is the same on the root of our tree.
Yes.
If you find directly the value there. Else, so if we just directly find the value there, we return true. And else we need to search on the children.
Yes.
And so we could actually like call this dot children contains again, because it is, we can use it like recursively, but if we have nested children, so we should call it like for every, yes, for every children. So like this, you have, okay, this dot children, which is an array, and you apply the sum method, and the sum checks to find if this value is somewhere in this array.
If you can, yes.
So for each one of the children, it will run the contains value. Okay.
Yes.
It will run the method contains value. Okay.
And for this, I think it's similar than this and the binary tree. And I tried to do like this, but it's not working. I didn't understand how this working that is.
For the trees, the traversal.
Traverse, yes. I didn't.
The
I did just do exercise because the
okay.
rest. Okay.
For the contains, does anyone have any other solution or any ideas?
I have it, but I don't know. I didn't check if the test passed. But I kind of structured it similar to the for loop that we did in class.
If you want, you can share also a screen and show us, just to see different, because there are many ways, yes, to implement it. Okay, yes. Sorry, Charlene, we cannot see, hear you. You are muted. So this is similar, yes. So first you check to see if it is on the root. And then for each child of the tree, you again call the contains method for them.
Yes.
Mhm.
So I'm not sure if this one works, but I kind of structured it so that it would call like the child, and then it would call for everything each time there's a child to this dot children. And if that is true, then it would return true. Otherwise, it would return false. But my tests aren't passing.
So one thing here that you should change is the return false. It should
Mhm.
be outside the for loop, because if not,
Okay.
the for loop will be done only for the first child. So for the
Okay.
first child, it will check, and if it contains, it will return true, else it will return false. But then it will not continue for the rest of the children. It will
Okay.
immediately assume that it's false. So yes, like this, it should work.
Okay. And then I didn't do the rest of it.
Okay.
I also found that one hard.
Nice. Okay. Anyone has the traverse or want to show a take on the traverse function?
I have the traverse I can show.
Okay.
Let's see. Can you see my screen?
Yes.
Okay, so the traverse, I apply the function to the tree and then rotate through all the children and apply it again. And
Mhm.
it worked.
Yes, it's as simple as that. So I mean, in lines of code, it's not that much as you have it, but probably the recursion and thinking about it. So one thing here to notice is this fn this in line 42, so that you can also call a function when you just put this and not this dot value or this dot children. It means that you pass the whole tree. So you can also do this. This makes reference to the whole object that the class is creating. So when we want to just refer to a property of the object, we just say this dot value, this dot children, or this dot traverse if we want to refer to a method. But if we just want to pass the whole thing, then we can also use directly this. And so for the traverse, we first apply the function to the root, the callback function, and then for each of the children of the root, we call traverse again. And your tests pass, I assume, right?
yes, for traverse, it does.
Okay.
I really struggled with the next one because I felt like finding the value would be really similar to doing like the contain, because you're just locating it and then returning it instead of saying true or false. But I couldn't get it to pass the third test. Like it kept, I just basically did the same one instead of returning true or false, I had it return the node.
Mhm.
But for the grandchildren, it would only return the child. Like it would go one level too high, and not return the correct node. And I don't know why. So it passed the first two, but not the
And
last.
the other one, the nested grandchildren.
Yeah.
Okay. Return child, find value. So if return child. Okay. Before I go to the find, let me ask for traverse how the rest sees it, or if you understand what we're doing with traverse here. So we just go from the root node, apply something, a function that we can pass, different types of functions. So for this test, we were passing a function. I think that it was just pushing the value to an array. So we were just grabbing the value and they were pushing it to an array. But so we start with the root and then we called recursively, we call the same traverse for the children. Any doubts here?
I still have a question about the contains, actually.
Yes.
Because my solution is still kind of not working. And I'm not, yeah, I'm just not really sure what I'm doing wrong.
Okay, then let's see yours also and see if we can find the bug or what is happening.
I can share my screen.
Hmm. Mhm.
So if then else loops for the children, and then performs that check on the children.
Mhm.
If I can probably remove that here.
Mhm.
And then if that the above is true, yeah, it's true, returns true, then else it performs the function again. Or no, I should actually, yeah.
Mhm. Mhm. Okay, so you call this child contains value here 3 times. So it's which is not needed. So if you just like call it once and maybe store what it returns in a variable, then you will see how this is used. So when we call child contains something, it will return true or false. So in the line, yes. So for example, if you remove this line as you had it,
yeah,
as it is like this. So if child contains value is true, so that the inside statement of the if case, so means that if child contains value is true, so that means that you have found it, then you return true, which is correct. Else, it means that the child contains value, you have already called it and it returned false. Okay, because you have an if else here, and the first if calls child contains value, it checks, and it either returns true and you do the first line, the 36 line, so it returns true, otherwise it had returned false. So if it had returned false, there is no need to call it again because it will still return false. So you just need to, so if you do it like this and you else return false, that will work only for your first child. Is what we said before, yes, to Charlene. So the return false should be outside of the for loop. So it means that for each children, we check, for each child, we check if it returns true or false. But then if it doesn't find it in one, then it doesn't mean that the whole function should return false. It means that we should continue looking until we have finished the for loop, and then we assume that we have not found it anywhere, and then we return false. So here you can just, yes, if you remove the else as well. And now I think.
I think I'm missing.
Yes, I think it should be an extra bracket after the line 36. After line so that the return false is outside the for loop. So your for loop would just have the if. Like this, yes. I think this should work. So first you check it for the root, and then for each child, you call the function. If you find it, then you stop because you have found it. If not, you let the for loop continue. And when the for loop ends, if it's ending without any return, it means that it didn't find it. Because if it was found during the for loop, then it would have stopped the execution with the return true. So then we can assume that we did not find anything and we return false after the for loop.
Okay.
Yeah, so this return false, it's you will find it a lot. I think I have seen it also in many cases, so that the immediate reaction is to say that if true, then I return true, if false, then I return false. But it's not always the case, because maybe I have not found it yet, but I still need to continue searching, and that doesn't mean I need to stop my execution of my function. Because every time I call a return, it will stop the whole function, so it will not continue searching further.
Okay, thank you.
Okay. So let me go back. What was the find, right? That you had, Jacqueline, if you want, you share again your screen and we check again the find.
Sure. So my logic was that it's the same as contain, but that instead of returning the true or false, you return the node itself. But when I kind of console log to check it, it kept returning. It would only go 2 levels deep. It wouldn't go do the nested grandchildren. So I'm not sure why.
So you start, okay, so we start with if we find this value at the root, then we return this, because that means that it's the whole tree. So we return the node that the value is found is the root node. So we return this. Okay, and then if we did not find this, then we need to, as you say, go inside the children. So for let child of these children, same as we did before. And then if child find is true, if child dot find value, so we call recursively if child find value. So if this is, but this is not going to return true, right? If child dot find value, it will either return null, okay, or a node. Okay, so if it's not null, so if it returns a node, then we need to return the node that this find value have found, not the child. So child dot find value returns a node, but it's not, it doesn't return the child, it returns a node of the child that has this value that we are searching. So we should actually like return child dot find value.
So return what? This here?
Yes, this again.
Okay. Okay. Yeah. Thank you.
Yes, because what the find returns, it's a node that it's nested under child that contains the value that we are searching. So when we find this node, we need to return this node of the find. Yes. So yes, you can either like store it before and return it. Okay. For if I think it should work. Does it all the work, all the tests work now?
It
Okay.
passed them all. Thank you.
Okay. So yes, that was just this. Okay, some questions here or some comments. This is also the same as Jacqueline said. It was like contains, it's recursively the same thing. We search the root, then if not the root, then we go in the children of the root, and then recursively we call again find with this, with the children.
I have a question on the first if statement. Why do we return this for the find value?
Because we want to return a complete node, not just the value. So if this dot value is the value of our root node, of the root of the tree. And so if the root value is the one that we are searching, then we return the root as a node, so we return this. So every node is a tree, so actually we return the whole tree. What would be your intuition of returning? Return this dot value or?
Yes.
Yeah, so with this dot value, you would just return the value of the node, but not the whole node. And since the function asks for returning the whole node, that means that it's not only the value, but also the children. So it's a node on its own. It's a tree, basically, because the nodes that we are dealing with here are all trees. So we return this, we return the whole thing, not just its value.
And then is that why in the for loop we also have to return .find .value, because that returns the node rather than just the specific value?
So in the loop, we just return, yes, we return again what the find value returns, which is a node. So we need to return either a node or null. So yes, here we with the recursiveness, we let the child.find value return what it's going to return, which is a node, basically. If we check our base cases, we see we see what we expect the function to return, because if we check it recursively, sometimes it's more difficult. But if you see here, we have two base cases, one on the line 52 that returns a node when it finds it, and one on line 59 that if it doesn't find anything, it returns null. So these are the two base cases for this recursive function. So it will either find somewhere a node and will return the whole node, or it will return null. And then when we call it recursively, it again will return one thing or the other. So the find will always return either a node or null.
Thank you.
Anyone else managed with it find? Or you have some different take on this? Okay, did you manage to do the next, Jacqueline, or
No,
you got
not
until
even
there?
close. I tried, but no. Well, it kind of the
Okay.
same thing. Maybe it was returning, it kept returning the wrong node before, probably because for the same reasons.
Maybe, yes, so
Yeah.
maybe you should,
So,
yeah. Mhm.
So I don't know.
Yeah,
Instead of
I'll let you check it, don't
Yeah,
worry. You don't have to
okay.
like do it now under pressure.
Okay.
I can show you also,
Okay.
so let me show. Mm. So the find we have and the insert child under. So there were these two, insert child under and insert between. These two were optional. I think find was also optional. They were a bit more tricky, but I think this is the three tests. The insert, this is the insert child under method, okay. So in the insert child under, we take a reference value and a value for a new node. So it adds a node with value, with this new value, as a child of the node with reference value, and returns the new node. So again, we need to return the whole node, not just the value of the new node. Or null if reference value was not found. So first, I check if there is a node with a reference value. So find, we use the previous method find to check if there is in our tree a node that has this reference value, and I stored it somewhere. If not node has been found, then I return null, because there is no node with reference value to add the child under it. So directly I stop here and I said that there is nothing like this. And if not, I create this new node that it's a new tree with the reference value, not the reference value, the new value that I'm passing. And I add this with the add child. So using the node that I have found. So remember, this node makes a reference here in this line 62, which is a node that has a value same as the reference value. And I'm calling the add child method for this node to add under it a new node with the value. So in fact, this is a bit weird because this is done twice. I'm doing it here just because the function asks for returning the new node. But in fact, the add child method is also going to do the same thing. So if you remember in the add child, when we take some value, it also creates a new tree. So here in the add child, it also creates a new tree with this value. So it will create a new node with this value and will push it to the children. So I think here there is a bit of well, it's a bit weird with a test. If you didn't do it like this, it wouldn't pass. So we should either change the add child method to return the node so that we don't have to do it twice, or if not, you should do it like this. So first create the node so that you have some node to return, and then add it with the add child method. Sorry, this keeps popping up. So how do you see this? At least the ones that you tried it, if you did not try it, maybe you need some time to process it. If you have tried it, or you can follow it.
I have a question. Wouldn't that create like 2 times of, or actually not really. So if we use the find method, then it doesn't find it, then it would return null and then create the new child. Is that correct?
If we use the find method, so in the line 62, yes.
Yes. So it
If we don't
finds
find
it,
it.
and then if it's not there, then it's going to create the new node with this value, the second parameter that we have in this method. But what if it's already there? Because doesn't that mean if we have 64 and 65 doing the same thing, wouldn't that mean that when it does the find method, it would be double? I'm not really
Okay, so this thing is a bit redundant. This is just for the return to work. So for our test to work, because the return needs to have a node that returns the new node added. So it should return a node, and I did it like this so that it returns a node, but it is a bit redundant. And in fact, this node here that is created, it's like floating, let's say. It's not under this exactly node, it's not added on our tree. But it's not a real issue, because on our tree, we do have a node with this value added with using the add child method. And so we do have a node with this value, and then it's only added once, because here I'm just creating a node just to return it. But I don't have any, I don't have this node added to my tree, because I don't put it anywhere in any array of any children or anything. So I think this is a bit weird way of doing it. I just tried to do it quickly, because the solution that it was given, I mean, from the solutions I got, it was not working. So there was some kind of bug with the solution compared with the test. So there need to change something, either some of the tests or the add child method. So this was like a quick fix, but it's not the most elegant solution to create the node twice.
So if we actually had a return of the new node inside the add child method,
yes,
then we wouldn't need that, and we can technically.
Yes, you should. If you had the add child return the new node, then you could directly like do this. Basically, the solution that I got from, from the other instructors. So the solutions that we have, but I will ask them now to change this, because this actually doesn't pass the test.
Okay.
Because the add child actually doesn't return a node. It doesn't return anything. And so if you try to return this, then it returns undefined. And so there is some test here that it's not passing.
Okay, thank you.
But yes, that's
It's-
good catch.
But this way adds the new node to the tree, right? This way.
Yes.
The
So
other way
like
it was
this,
kind of floating.
like this is the more elegant because you directly take care with creating and adding the new node in the add child as it was done until now. So add child will take a reference value and will create a node and add it to push it to the array. But the problem is that the add child that we have done now, it doesn't return anything. So we should maybe modify add child to return the created node, and then this would work like this, which would be better, I think, more elegant as a solution. Okay, more questions? Oh, this is from before. And the last one, insert between. So in this case, we have a bit more of putting things around to do because we have two values, a reference value and a child value, which has to be a child of a reference value. And so we want to add a new node in between. So if we have some scheme in mind, maybe we have a root with 1 and then it has a child, let's say 3, and then we want to add 2 in between 1 and 3. So now 3 is not going to be a child of 1. We have to like cut it and keep it somewhere and then add the 2 and then add the 3 as child of the 2. So first of all, we check again if we find the reference value. If we don't find it, then directly we stop our execution and return null because we did not find the first of the values, the reference value. Then we create a new node with the value, the one that we want to add is this, the third parameter is the new child that we want to create. So we create this new node. And then we loop over the children of our reference node. So this node here, the one that we have found, supposedly with the find method. So this find returns a node when it finds it. So we have this node and we can loop over the children of this node. So for the length array, for the array of this length, we do our for loop. And then for each children, so node children I, we check if we find the child value that it was given. Okay, because the child value, the second value, makes reference to one of the children of our reference node. And so we loop over the children, we check to see if we find a child like this. And then if we find this child, then we have to store it somewhere. So we keep it. I named this keep. So we keep this node.children I, because we want to keep this sub branch of the tree somewhere. Then we push this tree that we have now kept to the children of our new node, because this new node will be in between, and this part of the tree will now be children of the new node that I inserted. And then I add the new node to the children of the original node. And I return new node. I don't know if here I'm missing to remove the children. Keep node children I. So the tests are passing, but maybe the test doesn't detect this. So I just add this. Yeah, so I cut the part of the tree. Maybe if we do it schematically, you would see it better. So we imagine that we have to add something in between. So we cut the part of the tree and we put it one level lower. So we add it to the children of the new node that are creating. So here with the push method, I'm adding this tree that I have cut as a children of the new node. And then I add this new node as children of my original node, so of my root node. So as to add this in between. And I return this new node that I created. And at the end, I have a return null because maybe this for loop didn't find anything. So for example, imagine that there was no children with this value, the provided value. So if my reference node had no children like this, then I cannot do this and I have to return null again, but outside the for loop. So I need to make sure that the for loop completes and it checks all the children. Okay, and so this works. I think I'm not sure if we need to pop this from the children array, but anyway, it seems to work, at least the test. Maybe there is a test missing. So sometimes the tests are not like perfect. Can be that there are buggy tests as well. Okay. Yes, it was a bit like linked list now that I see it. So you need to cut one and then move it and then add some things in between. So was the binary tree better or worse or? Okay, any volunteer for the binary tree for starting at least the easier parts? Let's see, binary tree. There's our common ancestor. Okay. Okay. I will show some of the binary tree. Interrupt me anytime, right? So the binary tree that we try to create is something like this. So we have here a scheme to help us a bit guide ourselves. Remember that a binary tree has just two nodes, a left and right. And so when we construct it, we have a value and a left and right children. So to start with the add value, it adds a node, but it's not as immediate as it was with a normal tree because it doesn't just push it to a children array. It needs to do the checking that we were mentioning. So when we get a value, we check, is it lower, higher, or lower than the value of the root? If it is less, if it is lower, then we go left. And if it is bigger, we go right. So when I want to add a value, I create a new node with this value. So I can call binary tree class and create a new node with this value. And then this new node, I need to see where to attach it. And so I check the value against the root value. This dot value, it's like my root value. And so if the value is less or equal than this dot value, then I go left and I do something left. Else, I do exactly the same thing, but right. So this and this, the if and the else are the same. It's just that if I go left or right. And so inside the if the node. So if this dot left, this means that if this dot left is not null, so I have some other node there, then I attach this new node under, well, not I attach it under, I delegate the decision to this node. So I call again the add method for this dot left. Now my new root will be this dot left, and I will check again the value against this new root. So I delegate the decision there. If there is something there, if there is nothing there, so directly this dot left becomes my new node. And exactly the same thing happens with the right. So again, if I go right, if I decide to go right because the value is bigger than the root, then I first check if there is something right. If this dot right is not null, then I call the add method for this dot right as my new root. So I add for this new subtree. Else, I just attach the new node to this dot right. This dot right, I make it equal to new node. How do you see this?
If the value is equal, it goes to the left. Is that right?
Yes, I think this can be decided. So less than equal or higher, or only less and higher than equal. So equal should go either one or the other way, and you can decide. And so the contains method, it should return true or false if the value is in the tree. So it should search again the tree. And first we check the root. If this dot value equals value, then we return true because we directly found it. Then if not, we check it in if this dot left, and then we call again contains value. So we go to the left tree and we call the contains value for the this dot left recursively. This thing here is just because this dot left may be empty, may be null. So maybe at some point I don't have any this dot left. And if I try to call the contains value to a null node, then it will give me an error. So I have two ways of doing it. This is like the short way. I could also do it in a more, so if this dot left and this dot left contains value. So it means I check that if there is a node on the left, and then I call the contains value to this dot left. And if it finds it, then I return true. Okay, and this is the same as this. So this question mark here means that if this is not null, then I will do the calling of a method. Because if I try to call a method to a null or an undefined property, then it will give me an error. Okay, so I can do it like this. So I can have like double check, or I can use the question mark. So I check it on the left, I check it on the right, and then if none of these above things returned true, at the end, I have a return false because it means I have not found this anywhere. So again, here I have a recursive case, and I have like two base or stop cases. One in the line 28. So if I find the value in the root that I'm currently searching, that will return true, otherwise it will return false. And then these two cases are both recursive. It will call the contains for a new root. And again, for the new root, it will either find the value there or call it for the left and right. And so it will go on recursively until it hits one of the base cases, either finding the value or returning false, because there is no left and right to check anymore. Do you have this done or some other way? Anyone managed to get here? And
I think what I
Oh.
did was I just with the if, I just checked if there's if this left or this right, and in the return statement put the function, which I guess is the same then. So
Okay,
if there's a
so-
left, no, yeah.
so yes, so if there is a left, then return calling the function for the left. This dot left contains true. And then for the right, the same thing, right?
Yeah.
Yes. Yes, that should work also. If this dot left. Yes, because this contains also will return true or false. And so you will return true or false. So yes, this is also correct. Mm-hmm. I think if I save it at least. Oh no, I now I have one that it's not working. Expect binary contains method. Expected true, received false. It didn't find something.
I had the same error.
Did you do it like this, the same way?
No, I did it another way.
And in your case, Mela, with this way, do they pass the tests?
Initially it was,
So this dot right contains value, and I have it contains 16 to be.
There's an error, Anna. The right has an.
Yes, here you are right. But still, it doesn't pass this one. So this left contains. Okay, I see what it's happening. I see what is happening. So this left contains value. Okay, so this contains method can return true or false, right? So that means that if we do it like this, our execution of the function will stop here. Either the contains of the subtree, it will have returned true and it will have find it, so okay. But if we have not find it on the left side, then this part will return false. And then my function execution will stop here because I have a return false and will never check the right part.
yeah.
So I need to stop it here only if it is true. If it's not true, I still need to do the second one. Okay, it's the same as we were saying with the for loop. So that's why, yes, if we do it like this, so it only stops, so it only gets here if this is true. If this is true, then yes, I return true. But if it's not false, it doesn't mean that I have not find it and I need to stop the execution. It means that I need to still check the right part.
Okay.
What about your solution, Tatiana? How did you have it?
I can copy, I can paste it.
And you say it gives you an error?
Yes, it gave me the same error like the 16. Expect binary tree contains 16 to be true. It's not going.
So you have it like this then. Let current equals this dot value. So here, I guess that you use new value instead of value, right? Because if not, this is not used anywhere.
Yes, I changed the name. Yeah.
So, okay. And so if new value equals to current, return true. So that checks for the root to see if we have find it there. Else if new value is smaller than the current, then I will check on the left. Okay, current is this dot left. But then you don't call again the contains.
Yeah, I think I stopped there yesterday because I tried and I found a solution online and I was trying to understand it, and then I think I stopped here because I see the problem was like I'm doing nothing, like
yeah, so here you should call again the contains with the new value for this new new root that you have now, and then check something. So this will return something, this contains will return true or false, so check this and then maybe return true if this has find it, or if not, don't do anything and wait for the next thing to happen as well. So in fact, this could go outside because the current return true. Still, I have one, but it's not, cannot read properties of. Okay, so maybe we have a case where this is null. So let me put it like this. And now it's passing also the tests. Okay, so I need to put this because maybe this left or this right doesn't exist. So it will be the current, then it will be null if I don't have all my tree created and there are no left or right at some point. But yes, you can do it like this as well. You were missing basically this part of calling again recursively for the new root. So you were deciding here if like the new root that you will check is this left or this right, and then you store this to this current as a new root, but then you need to call the contains method to this new root. Okay, questions? More different ways of doing it if someone else has tried it.
I don't really get the question mark again. I missed
Mhm.
your explanation on that.
Yes, so this is equivalent to if current. So if current is not null, basically, because see here how current we set it to this left or this right, but maybe this left or this right is null at some point, because at least initially they are null, and depends on the value that we got. Maybe we don't have all the three balanced, so there is not always a left and a right. Maybe there's only right children at some point, depends on the values that we get. And so if this left or this right is null, then whenever we try to use them, we need to check if they are null. So we assign it to current, but maybe current is null. And if current is null, then we cannot call the contains method on a null property. It will give us an error. And so we either have to make sure that there is not null. So we have a node there. So if we have a node, then we call the contains method for this node. Otherwise, we don't. It doesn't make sense to call the contains to a null. So we can do it like this, or we can put the question mark here, and it also means that if this is not null, then call the method on this.
So it's just a shorthand way.
Yes, yes, it's like a shorter way of writing it instead of like doing the double checking first if it's null and then calling the method. You just do it like in one line.
Okay, one last question, sorry.
Yes, no worries.
With the question mark, it checks first whether there's null or not, and then if there is a null value, then it will not run the code. But if there is a value inside of that, then it will run that code so it doesn't throw an error. Okay, thank you.
Yes, so first it checks, and if it is null, then it will not run this. So automatically this will be like a false if case, and then it will not do anything. Else it will call the method and then check again, of course, what this method returns, because then maybe this returns null. So here we have, or it will turn false, I mean. So it's quite useful when you don't know for sure if this will have some value, and you want to make sure that you check before if this is really something that it's valid. It does not, if it's not undefined, it's not null, and then you can use it for calling methods on this. How was it, Monica? Did you manage to do any here on the binary tree?
I did it different, I think. I will send, okay.
Yes. Okay, let me check. Mhm. Return false. What did I copy? Oh. Contains value. It's a bit too hard copying from here from chat. Okay. Now I have it. Let me just put this in comment and see your contains, and it also passes the test, right? In your case?
Yes.
Okay. So again, we start with checking if the value that we are searching is on the root, and then we directly stop the execution and return true and else. And you check if left and right are not null. If both of them are not null, return this left contains value or this right contains value. So you will return this or this. So it will be, if either one gives true, then you will return true. Else, if one of them gives false, it is an OR. So how does this work? So, and then why do you repeat it here again? So if, or maybe you can try to also explain your code, right?
Yes. Because I needed to check the right and the left, because the when is use the first if is not working for the next. It's just the right. If it's the right, not checking the left. And I needed to put in the right and left for both.
So one thing I see here is that this thing, so calling contains here,
Yes.
you don't actually use it anywhere.
Yes.
So if you have a node on the right, then you call contain, but this will return something, and the return of this is not used, at least here. So you don't catch if this returned a true or a false.
Yeah.
You just call it. So if you didn't have this part, it's not working.
It's not working, no.
Okay. I think it's not working because since this is a
For the
NOR,
OR? For the OR?
maybe. So let me see. Oh, now it's working like this. It seems to be working, at least the tests with the contains method, they all pass like this.
Oh, yesterday I didn't work.
Okay. So yes, like this, you do it for both left and right, and you catch what both return. And so if both return, well, both cannot return true because the value cannot be both on the left and on the right. So there is a case of both returning false. And so false or false will be false and you will return false. And then there is a case of one of them returning true, and true or false will also be true. And so that's correct also, yes. So it will return the desired result. Yes, I think like this also, it works, and it's even shorter.
Okay.
This left or not? Let me check. Maybe we could also make it work with a question mark and just avoid this, or we don't have to risk too much like this. No, now it's not working. Okay, well, let's forget about this part. Okay, so yes, I think the important thing with the recursion is to understand this, that when you call a function recursively, you need to catch what it returns. So this function is returning something, and even though it will return it when it's called, like on the inner level, I need to also use it on the function that called this, so on the outer function, let's say, because at the end, the test is calling the outer function, and the outer function will call the like help for help recursively, will call the function again and again, but then it has to use what the inner calls return to have the final decision. So the final decision is done like on the top level of this recursive pyramid. So when this returns something, you need to catch it. If you just call this, then it will not work. That's what I was trying to like explain when we were doing on the Slack with the question, but I don't know if if it got understood. So when you call a function recursively, you need to reach the base case and then go back on the top call. So go back on the top call, and then the top call will have the final return to stop the execution. Even in the intermediate step, you have some return, you need to catch it on the upper levels. Okay, so we have 3 different ways of doing this. Nice. How about the rest? Did you try it? Rebecca, how did it go? Do you have any go on this?
I tried the first one and I attempted the second one and I gave up. I feel really lost right now with the trees. I mean, it's making sense. It's making sense now, but as I was working through it, I was having a really hard time.
So the add method you managed to do, and then the contains was a bit tricky.
The contains was a bit tricky, and then I was trying to do
the recursive part that it's tricky.
Yeah, I feel like I didn't really have a good grasp of recursive yet, and then I was trying to do this thing that I now know I can't do because I was Googling it. I was trying to use the or. I was trying to do it for 3 times instead of just 2 times. I was trying to make that work, but yeah.
Okay. Sorry. What about, let's see, who else I didn't ask? Gabriela, how did it go?
I could do the add one, and in the contain, it was sort of like the same thing that you're doing here, but it wouldn't work because I didn't understand what you were trying to say. Like I went through the Slack and I just like didn't understand what you meant by sort of like saving the return. So I just like gave up there. So I think I need to sort of like go through it again.
So I don't know if there is a better example for this. No, because this doesn't return anything.
I just get confused with the returns all the time. Like I don't know when to use it or where. I mean, I know where in terms of like if it needs to be outside or inside, but not really like when we need a return or not.
Yes. Okay, let me check on the Slack what we were saying yesterday. I don't know if it will make any sense. So this thing, at least that I was saying here. So this example that I was giving, so we saw this on the slides, and this is not a recursive function, but it could be. So it's the same with recursion as well. So you have a function that calls another function inside this, and this say hi function on its own returns something. It says return hi, but this high, we will not see it anywhere in the console or anywhere, so we cannot use it unless we use it in the function that called it. So this say hi to me now actually uses this return, because in its return, in the return of this outer function, it uses and it adds it to something. So it's using this return. If I did not use it and I just called say hi here, so in this case,
Your screen.
you don't see the screen, sorry. Why not? I was not sharing. I was sharing. I think, let me share again. Now, yes.
Yep, all good.
Okay, sorry. So yes, as I was saying, we have these two functions and one is calling the other, and the same happens with recursion. And when you call the say hi, then say hi may have some return, but this return is useless unless we use it in the outer function. So here we do use it because the return of the outer function is using the return of this inner call and add something to it. And then we see hi and the name. But because we use this return to create this string. If we simply called say hi, like here, I call say hi and then I return something, but see here in this case, I don't actually use the return of this. I don't save it to any parameter. I don't store it and I don't use it to create some other string or something. So I cannot expect just because I call this function and that this function returns something, this something is lost unless I use it in the outer function. Okay, so this the outer function, the one that called it, needs to store this somewhere and do something with this return of this inner function. Okay, if not, say hi, we'll have created something, maybe did some operations and returned some result, but like no one is listening to what it returned. And I return name and I simply then this say hi to me, just returns name actually, even if it called it or it didn't call it, then there was no change. There was no effect. So the same thing happens when you do it, try to do it recursively. So when you call the recursive function inside, you need to use what the recursive function will return. So it's like what we were saying. So if it is this, how is it called? Broken phone or broken, when someone says something to the other, you know, and you wait to get back from him. So when I get back from the other person, I need to use what the other person told me and pass it to the next. If not, the chain is broken, let's say. So I think I will try to find some better with recursion. So this was not with recursion, but I will try to find a better case with recursion, or maybe same here. We have, I think we had a good example here. So, yes, which was what, share. So basically it's this code, what Crystal was trying to do with the contains. So I will copy this. I think this was for the tree, right? And not for the binary tree. This was the contains here that you were doing. Right, so this was, let me put this in comment. And here the tree test. Should return the contains, it's defined. No, now many of them are not working because they depend on the contains method, but where's my contains test? Okay, this is the contains test. Okay, just to make sure we have this clear, I think this is more important than going to the rest of the activities. So we'll try to clarify a bit this, and then we go to the graphs. And so here, if you check these two solutions, the one that like I gave you and this one, they are pretty much the same, just that what Crystal was trying to do was, again, recursively, we check for the root, and then for each one of the children, we call the contains method. But calling the contains method in here, we don't use what the contains method returns. So remember that the contains method will reach some base case and will return false at some point, or it will return true if it finds the value. So if I just call it, I don't know, I don't hear what the contains said. The inner contains method. So when I called it inside in the recursion again and again, so imagine like a pyramid, and it's again and again, and it's called, and at some point the inner contains method has returned true, has returned, I found this value that you are searching for. Okay, so this has returned that I have found it. But the outer method, the mother method that called this recursively, does not pay attention to what this said. So here I don't really know if this has found something or not, because I don't catch what this method returned. So I'm asking to all of my children to search for a value. And so I tell them, search for this value by using the contains method. And then they respond that I have found it or I have not found it. But if I don't check this, so like do some kind of, let's say, like this, store it in a parameter, and then maybe check if they have found it, then return true, for example, something like this. So to try to use what the recursive calls have told me, have gained back as a result. Okay, so if I don't use it, then it's lost. The effort that was done by this recursive function, it was not really useful. So you see that in between this is just this, the small detail is just this, that here I'm actually using, because in this if case here, I'm checking what child contains value has told me. So since it is inside an if case, it means that I'm checking if this has returned true or if this has returned false. So I'm using what this has given back as a result, if has found the value or if it has not found the value. And then I act accordingly. So maybe I return true, or maybe I continue with my for loop or whatever. So I delegate not the decision, part of the work, I delegate it to the recursion function. And then I see what this recursion function has given back, and I continue with my work. But if I delegate the work and I don't see what it returned, then it's not really useful. So if you want, I don't know if you have some questions now, or if you want to check these two things and simply check what is the difference that this makes. So why here it's not working and here it's working, right? So that's, I understand what I mean by catching what the recursive function returns. And this is the case when a function returns something, because maybe we have a function that doesn't return something. So then this is different. If a function doesn't return something, so we had this add child, that it didn't return anything. It just pushed a value to an array. So then I don't have to catch the return because there is no return. This function is doing something that means affecting maybe a global array variable. So it will do it anyway. It will do, part of the job is like write something to the array. And then when I call it recursively, it will do the job. It will write something to the array. It will not return me something. And so in this case, it doesn't matter. I could like call add child and don't store something anywhere. I mean, the return anywhere, because it doesn't return anything. But if it does return, so if there is a function that does return something, then I need to store it, use it, etc. Sorry, you were about to say something and I interrupted you.
Yes, I just wanted to ask, because I had the idea that once you had a return that will stop the execution and then the following part wouldn't really run. So in the case, I think it was like the binary tree contains, the moment that you have the return this dot right contains, wouldn't that stop everything and we'll never get to the return false that we have outside?
Let me check the binary tree. So in the contains here, so you, for example, in this one that we were, that we had originally. Let me just like remove the other solutions and we leave this. So in which case you mean?
In that in that one that you just
Okay, so you meant in this version.
for example, there's
Yeah, I think they are similar, but anyway, yeah, so let me comment this.
like wouldn't line 40 with that return stop the execution of line 43?
Yes, it will stop it if yes, so this is not else and true. If this left is not anything, return. In this case, in this version, I think this is not really needed because the return false will be done in here. But I'm not really sure. I need to check. This is the one, I think this is the version that Monica sent. And now, no, if I drop this, and then it's not working. So this, when there is a return, but it is inside the if case, so in a more general note, if it is inside the if case, that means that, yes, it will stop, but only if this is true, because maybe this is not true. And if this is not true, then it will not stop here. It will go to the next one. Because this is inside the if case, that means if both left and right are not null. So if this happens, then yes, this will return something. It will return either true or false, and then here it will stop. But if not, both of them are not null, then this if will never happen. And so this return will happen. When we have a return inside a conditional, it means that it's not going to run always. So, so the same happens. So let's see in this example. So here I have various returns as well, 1, 2, 3, 4, but not all of them, of course, will happen because since they are all inside, all three at least, they are inside conditionals. That means that they will only happen if the condition is true. So this return will happen only if this is true. So if we have a left child and that this left child contains the value. If this is not true, then this return will not happen and we will go to the next line and then it will check something else. And if this is true, then this return will happen. And if not, we will go here. So even if we have many returns, doesn't mean that all of them, only one return will happen for sure. Because as you say, at the moment that one return will happen, it will stop the execution.
Okay, thank you.
But if we have a return happening inside like a recursive function, so in the recursive call, it will stop the execution of the recursive call and it will get back to the function that called it. So remember the call stack. So we have function, calling function, calling function, calling function. And so when at some point one of the recursive calls stops because it hits a return, only that call will stop and then we will get back to the function that called it. It doesn't mean that all of them will return automatically. So it will return this sub function that we called. It will return something to the function that called it. And then this will return something to the function that called it. So the execution will stop, but progressively. It's not that one return will stop everything. Okay. More questions? Or as we discuss this more, you get more and more confused. But then when you review it, maybe you will clarify it more. So
quick question on the
Yes.
formatting. I don't know what is the advantage of doing if statements one after the other versus just doing like the if else if that we learned at the beginning.
So like this, you mean?
Yes.
So sometimes we try to avoid the else if it's not necessary. It's just, it makes it a bit easier to read. So for example, here I know that if this is true, it will return true, and then it will stop the execution of this function. So I don't really need to put else, because it's already implied that if this has not happened, then I will go to the next lines, and so on. So if you
I think
compare this,
I mean it differently from how you understood.
yeah.
I just mean if why are we putting 3 ifs in a row rather than if, else if, and then else if?
So if they are not directly connected, then maybe it's not an else if. Maybe it means that both can happen. So it depends. So in this case, we could have else if here. So if this is found, then return true. Else, if it's found here, then return true. And then else if return true, and even have an else here. And this will be all 4 cases, and it will still work the same. It's kind of optional, because it's the same thing as writing the 4 ifs. Just the else if sometimes it's a bit more hard to read, because it means that you have to make sure what happened before, etc. So it's just we try to avoid the else's if are not necessary. So for example, in this last case, I don't really need to write else, because this line will happen only if all the others have not happened anyway, because if not, some point a return would have returned and would have stopped the execution. So I don't really need to write else. It's already implied. I have arrived here because nothing of the above has happened. So it is kind of an else case.
Okay, thank you.
Okay, these are binary trees. Okay. So there were these ones also, the traverse depth first and breadth first, and then the lowest common ancestor. Since we are running a bit late, I'm going to pass you this solution, and we can check it, or you can check it and send me any questions, or I can also try to record something to go over those. Okay, so that we don't spend all our time in trees, and we do some graphs as well. Okay. Any last questions, or we take a small break, like 5 minutes to clear a bit our mind, and then we go with graphs? Okay, see you in 5 minutes.